almost 150 years before actual atomic theory was established. Boyle, Newton, Bernoulli and several other scientists tried to explain the behavior of gases. They considered that gases are made up of tiny atomic particles. Later in the 19th century, Maxwell, Boltzmann, and others successfully developed kinetic theory. Kinetic theory explains the behavior of gases based on the idea that gas consists of atoms or molecules which are in constant random motion. Kinetic theory has widespread applications. This theory leads to the molecular interpretation of pressure and temperature of a gas. It is also consistent with gas laws like Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's hypothesis. Kinetic theory helps explain the specific heat capacities of many monoatomic, diatomic, and polyatomic gases. It relates the measurable properties of gases like viscosity, conduction, diffusion to the size of molecules. In fact, these relationships help in the estimation of molecular sizes and masses. The atomic hypothesis is one of the most important theories ever proposed. What is the atomic hypothesis? According to the atomic hypothesis, all things are made up of tiny particles called atoms. These tiny particles move around in continuous or constant motion. Atoms attract each other when they are separated by small distances, and repel each other when compressed into one another. Atomic theory is credited to John Dalton. Dalton's atomic theory states that all matter is composed of atoms. Atoms cannot be made or destroyed. All atoms of the same element are identical. Different elements have different types of atoms. Atoms of two or more elements combine to form chemical compounds. In fact, Dalton had proposed atomic theory to explain the law of definite proportions and the law of multiple proportions, which are obeyed by elements when they combine to form compounds. The law of definite proportions states a given compound always contains the same proportion of elements by mass. For example, consider a water molecule. The ratio of the mass of oxygen, MO, to the mass of hydrogen, MH, in a water molecule is always fixed and is independent of how the water molecule is formed. The law of multiple proportions states that when two elements are combined to form more than one compound, then for a fixed mass of one element, the masses of the other elements in different compounds are in the ratio of small integers. For example, carbon and oxygen combine to form two compounds, carbon monoxide and carbon dioxide. If M1 is the mass of oxygen that combines with M units of carbon in the carbon monoxide, and M2 is the mass of oxygen that combines with M units of carbon in carbon dioxide, then, according to the law of multiple proportions, the ratio M1 is to M2 is a simple ratio of small integers. Dalton's atomic theory, when combined with Avogadro's law, helps explain Gay-Lussac's law. Gay-Lussac's law states that when two or more gases combine chemically to form another gas, then the ratio of volumes of the gases are in the ratio of small integers. And Avogadro's law states that at constant temperature and pressure, equal volumes of all gases contain the same number of molecules. An interesting thing to note here is that Dalton's atomic theory is also known as the molecular theory of matter, as the elements are often found in the form of molecules. Generally, the size of an atom is about an angstrom unit, which is equal to 10 raised to the power minus 10 m. In solids, the interatomic separation is very small, approximately 2 angstrom, whereas in liquids, the atoms are separated by 2 angstrom, but the atoms of liquids are less rigid than those of solids, and hence the liquid can flow. Whereas in gases, the interatomic separation is very large, approximately 10 angstrom. In solids, the atoms are tightly packed. That is, the interatomic force is strong. In liquids, the atoms are loosely packed. That is, the interatomic force is weak. Whereas in gases, atoms are very loosely packed. That is, the interatomic force is negligible. Due to interatomic forces, solids have a definite size, shape, and volume. Liquids have definite volume but no definite size and shape, and gases have neither fixed volume nor definite size and shape. The molecules and atoms of matter can be seen through electron microscopes and scanning tunneling microscopes. So we now know that atoms are divisible and are not elementary. An atom is made up of a nucleus in the center and electrons revolving in orbits around the nucleus. Protons and neutrons together make up the nucleus of an atom. These protons and neutrons are further made up of quarks. It is believed that quarks may be further made up of string-like elementary entities. In case of gases, interaction between molecules is negligible, except during a collision because the molecules are far away from each other. So, it is easier to study properties of gases such as pressure, temperature, and volume compared to that of solids and liquids. Gases at low pressure and high temperature satisfy a simple relation. PV is equal to kT, where P is the pressure, V is the volume, T is the temperature in Kelvin scale, and K is the proportionality constant. Let this be equation 1. For a given sample of gas, K is constant and can be written as K is equal to N multiplied by Kb, where N is the number of molecules in the given sample. From observation during various experiments, it is clear that the value of Kb is constant for all gases and is called the Boltzmann constant. Its value is 1.38 into 10 raised to the power minus 23 joules per Kelvin. Substituting the value K is equal to NKb in equation 1, PV is equal to kT. We get PV is equal to NKBT. Let this be equation 2. We know that 1 mole of gas contains an Avogadro number of molecules denoted by Na. So, N is equal to N into Na, where N is the number of moles of the gas present. Substituting the equation N is equal to N into Na in equation 2, PV is equal to NKBT. We get PV is equal to N Na into KBT. Upon rewriting the terms of the equation, we get PV is equal to N into NAKB into T, which can be written as PV is equal to nRT. Let this be equation 3. In equation 3, R is equal to Na into Kb is called the universal gas constant. the value of R is 8.314 joules per mole per Kelvin. This value is constant for a given system of units. Equation 3 is also called the ideal gas equation. A gas that satisfies the ideal gas equation at all temperatures and pressures is defined as an ideal gas. The concept of an ideal gas is merely a theoretical concept. In practice, there is no ideal gas. If we plot a graph by taking pressure on the x-axis and PV by NT on the y-axis, the graph is a straight line parallel to the x-axis for an ideal gas. That is, the value PV by NT is constant even when pressure changes. The behavior of a real gas at 3 different temperatures is shown in the figure. From the graph, it is clear that all the curves approach the behavior of an ideal gas at low pressure and high temperature. This is because at high temperatures and low pressures, the molecules of the gas are far apart and interaction between the molecules is negligible. From the ideal gas equation, we can say that at constant temperature and pressure, equal volumes of different gases contain an equal number of molecules. That means for an ideal gas, V by N is constant. This is called Avogadro's law. Let V1 and V2 be the volumes of a gas and N1 and N2 be the number of moles of the gas. If they are at the same pressure and temperature, according to Avogadro's law, V1 by N1 is equal to V2 by N2. 1 mole of any gas can occupy a volume of 22.4 liters at STP. And it contains Avogadro's number of molecules. That is 6.02 into 10 raised to power 23 molecules. The mass of 22.4 liters of any gas at STP is equal to its molecular weight. Thus, the number of moles in a gas is calculated by using the formula number of moles N is equal to the weight of the gas in grams divided by its molecular weight in grams. As the mass of a given gas M increases, the number of molecules N also increases. That is, M is directly proportional to N. A mass of 1 mole of a gas is called molar mass, denoted by M0. It contains an Avogadro number of molecules, denoted by Na. Then, M divided by M0 is equal to N divided by Na. If the number of moles and temperature is constant in the ideal gas equation, then PV is constant. That is, for a given mass of gas at a constant temperature, pressure is inversely proportional to its volume. This is called Boyle's law. According to Boyle's law, the graph between pressure versus volume is shown in the figure. Boyle's law is also satisfied at high temperatures and low pressures. If the number of moles and pressure of a given gas are kept constant, then the ideal gas equation can be modified as volume of a gas is directly proportional to its absolute temperature. That is, V is proportional to T, and V divided by T is constant. This is called Charles' law. If we plot a graph by taking volume on the x-axis and temperature on the y-axis at 3 different constant pressures, the graphs are as shown in the figure. In this case too, the graph is well fitted at high temperature. That is, a straight line, but it is a curved line at low temperatures. This is according to Charles' law. Consider a mixture of non-interactive gases in a container. At a constant temperature T, pressure P, and volume V. Let N1 be the number of moles of the first gas, N2 the number of moles of the second gas, and N3 the number of moles of the third gas, etc. then the equation of state for the mixture of the gas is PV is equal to N1 plus N2 plus N3 and so on into RT. Let this be equation 4. But if we apply the ideal gas equation to the individual gases, we get P1V is equal to N1 RT. P2V is equal to N2 RT. P3V is equal to N3 RT and so on. Then N1 is equal to P1V by RT. N2 is equal to P2V by RT. N3 is equal to P3V by RT and so on. Substituting the values of N1, N2, N3 in equation 4, we get PV is equal to P1V by RT plus P2V by RT plus P3V by RT plus so on into RT. On simplification, we get P is equal to P1 plus P2 plus P3 and so on. That is, the total pressure of the mixture of gases is equal to the sum of individual partial pressures exerted by all the gases. This is called Dalton's law of partial pressures. From the microscopic point of view, an ideal gas is defined by making the following assumptions based on the kinetic theory of gases. The postulates are: a gas consists of a large number of small particles called molecules. The number of molecules are of the order of Avogadro's number. The molecules are in constant random motion and obey Newton's laws of motion. The rapidly moving particles constantly collide with one another and with the walls of the container. All these collisions are elastic and of negligible duration. That is, in the collisions between the molecules and the walls, the total momentum and the total kinetic energy are conserved. The interaction between the molecules is negligible except during a collision. That is, the intermolecular forces are negligible because the average distance between the molecules is large compared to the size of the molecules at ordinary temperature and pressure. It is also assumed that the volume of the molecules is negligible compared with the volume of the container, and the molecules are perfectly spherical and elastic. Now, let's derive an expression for the pressure of an ideal gas based on kinetic theory. Let us consider a gas in a cubical vessel with the length of a side L, and the walls of the vessel perfectly elastic. Take the X, Y, and Z axis to be parallel to the sides of the cube, and call the faces perpendicular to the X-axis A1 and A2. The area of each face is equal to L square. These two faces are parallel to each other. Consider a molecule in motion and assume that its velocity along the x-axis is Vx. If this particle collides with face A1, since all the collisions are elastic, it rebounds with the same speed in the opposite direction. Let the mass of a molecule be m. Then the initial momentum of the molecule along the x-axis, Pi, is equal to mvx. The final momentum of the molecule along the x-axis, Pf, is equal to m into minus Vx, or the final momentum of the molecule along the x-axis, Pf, is equal to minus mvx. Therefore, the change in the momentum of the molecule is delta P is equal to final momentum, Pf, minus initial momentum, Pi. That is, delta P is equal to minus mvx minus mvx. Thus, delta P is equal to minus 2 mvx. As the collision is elastic and momentum remains conserved, the momentum imparted to the wall of the cube for one collision, delta P dash, is equal to 2mvx. Let this be equation 1. If the molecule travels with a constant velocity minus vx along the x-axis and without any collision with the other molecules reaches phase A2, then the displacement of the molecule along the x-axis, that is, the distance between phases A1 and A2, is L. Then the time taken to travel from A1 to A2 is equal to L divided by Vx. The molecule, after colliding with phase A2, rebounds and travels towards A1 with a constant velocity component Vx along the x-axis. The time taken to travel from A2 to A1 is also equal to L divided by Vx. Assuming that there is no collision with the other molecules, the time interval between two successive collisions of a molecule with phase A1 is delta T is equal to 2L divided by Vx. Then the number of collisions of this molecule per unit time is C is equal to 1 by delta T, which is equal to Vx by 2L. The total momentum imparted per unit time to phase A1 with this molecule is equal to C into delta P dash. According to Newton's second law of motion, the total momentum imparted per unit time is equal to the force exerted on phase A1 due to this molecule. Therefore, the force exerted by one molecule delta F is equal to C into delta P dash. The force due to this molecule is Vx by 2L into 2mvx, which is equal to mvx square by L. As there is no preferred direction of velocity of the molecules in the vessel, the motion along any one of the three axes is Vx square is equal to Vy square is equal to Vz square is equal to 1 by 3 into Vx square plus Vy square plus Vz square, which is equal to 1 by 3V square. So the force due to this molecule is delta F is equal to 1 by 3 mv square by L. Let the given sample of gas contain n number of molecules. Then the mass of the total gas is equal to the mass of one molecule, m, multiplied by the total number of molecules, n. The average square velocity of all the molecules of the gas is equal to the sum of the square of the velocities of individual molecules divided by the total number of molecules, that is, V square bar is equal to V1 square plus V2 square plus so on plus Vn square the whole by n, which is equal to sigma V square by n. Then the total force exerted on the face due to the total molecules is sigma delta F, which is equal to sigma 1 by 3 mv square by L, equal to 1 by 3m by L into sigma V square. Multiplying both numerator and denominator by n, we get F is equal to 1 by 3mn by L into sigma V square by n. Pressure is defined as force per unit area. Pressure acting on face A1 is equal to force divided by area of face A1. By substituting the value of force in the equation for pressure, we get pressure is equal to 1 by 3mn by L cube into sigma V square by n. Simplifying, we get pressure is equal to 1 by 3mn V square bar by L cube, where V square bar is the average of the square of the velocities of the molecules average of V square. And N by L cube is the number of molecules per unit volume, known as the number density, denoted by the capital letter N. And V square bar is the average of V square. From the kinetic theory of gases, the pressure exerted by a gas is equal to 1 by 3 mNV square. The expression for pressure exerted by a gas has been calculated by taking a cubical container. The expression is true for a container of any shape, because in the final expression, the terms representing the area A and time delta T are not present. While deriving the expression for pressure, we have not considered the collisions among the molecules. If, due to collision, the velocity of the molecule changes, there will always be a molecule that acquires the same velocity as that of the molecule under consideration. Overall, molecular collisions will not affect the above calculation. It is necessary to know two basic concepts: RMS speed and translational kinetic energy, to understand the kinetic interpretation of temperature. RMS speed is root mean square speed. It is defined as the square root of the mean of the squares of velocities of all the molecules in a gas. It is denoted by VRMS. Let there be n molecules in the sample and their velocities V1, V2, V3, and so on, Vn. The mean of the square of the velocities is equal to V1 square plus V2 square plus V3 square plus so on, Vn square divided by n. That is, V square bar is equal to sigma V square divided by n. Then, the RMS speed is denoted by VRMS is equal to the square root of sigma V square divided by n, which is equal to the square root of V square bar. This can be rewritten as VRMS square is equal to V square bar. Let this be equation 1. Now let's understand the translational kinetic energy of a gas. If the mass of each molecule is m and is moving with the velocity v, then the translational kinetic energy of the molecule is K is equal to half mv square. Total translational kinetic energy of all the molecules is K is equal to sigma half mv square. If the numerator and denominator on the right side of the above equation is multiplied by n, this can be written as K is equal to half mn multiplied by sigma v square by n. The mass of all the molecules is mn, which is equal to m. Then the total kinetic energy, K, is equal to half mv square bar. But, as per equation 1, VRMS square is equal to V square bar. On substituting, we get the total kinetic energy as K is equal to half mVRMS square. Let this be equation 2. Now, we can express the temperature of the gas in terms of kinetic energy. We know that from the kinetic theory of gases, the pressure of an ideal gas, P, is equal to 1 by 3 mNV square bar. Let this be equation 3, where N is the number of molecules per unit volume. Let V be the volume of the gas. then the total number of molecules of the gas is N is equal to N multiplied by V. By multiplying both sides of equation 3 by V, we get PV is equal to 1 by 3 mNV multiplied by V square bar. Since the total number of molecules of the gas N is equal to N multiplied by V, this equation can be written as PV is equal to 1 by 3 mN multiplied by V square bar. But the total mass of the gas M is equal to M multiplied by N. Then the above equation can be written as PV is equal to 1 by 3 M multiplied by V square bar. By substituting the value of V square bar from equation 1, we get PV is equal to 1 by 3M multiplied by VRMS square. By multiplying the numerator and denominator on the right side of the equation by 2, we get PV is equal to 2 by 3 multiplied by half MVRMS square. By substituting the value of half MVRMS square from equation 2, we get PV is equal to 2 by 3 multiplied by K. Let this be equation 4, where K is the total kinetic energy of all the molecules of the given gas. We know that the ideal gas equation is PV is equal to NKBT, where N is the total number of molecules of the gas, and Kb is Boltzmann's constant. By comparing the ideal gas equation with equation 4 and rewriting the equation as 2 by 3K is equal to NKBT, we get the total kinetic energy of all the molecules of the gas as K is equal to 3 by 2 NKBT. The average kinetic energy of a molecule is K by N is equal to 3 by 2 kBT. The average kinetic energy of a molecule is proportional to its absolute scale of temperature. That is, K divided by N is proportional to absolute scale of temperature. From the above expression, we can say that the average kinetic energy depends only on the temperature of the gas and it is independent of the nature of the gas. If the given gas is a mixture of non-reactive ideal gases, then the total pressure is due to all the gases present in the mixture. Let N1, N2, N3 be the number of molecules of each gas, and M1, M2, M3 be the masses of each different type of molecule, moving with velocities V1, V2, V3 respectively. From the kinetic theory of gases, the expression for the pressure of a gas is equal to 1 by 3 mNV square bar. When applied for the mixture of the gas, P is equal to 1 by 3 multiplied by M1 N1 V1 square bar plus M2 N2 V2 square bar plus M3 N3 V3 square bar and so on, which can also be written as 2 by 3 multiplied by half M1 N1 V1 square bar plus half M2 N2 V2 square bar plus half M3 N3 V3 square bar. We know that the average kinetic energy of a gas molecule is equal to 3 by 2 kBT, and this is the same for all molecules at a constant temperature. That is, half m1v1 square bar is equal to half m2v2 square bar is equal to half m3v3 square bar, and so on, is equal to 3 by 2 kBt. On substituting these values in the equation for pressure, we get the total pressure P is equal to N1 plus N2 plus N3 plus so on multiplied by kBt. In this equation, each term represents the pressure exerted by the gas, and on the whole, the total pressure is equal to the sum of individual pressures. This is nothing but Dalton's law of partial pressures. Let us consider an example. Calculate the RMS speed of a molecule in oxygen at 27 degrees Celsius. We know that average kinetic energy is equal to 3 by 2 kBt, and average kinetic energy is also equal to half mvrms square. Given T is equal to 27 plus 273, which is equal to 300 Kelvin. 1 mole of oxygen contains Avogadro's number of molecules. That is 6.02 into 10 raised to power 23 molecules. The mass of an oxygen molecule is equal to the molecular mass of oxygen divided by Avogadro's number. By substituting all the known values in the given formulae and by equating the formulae of average kinetic energy, we will get the RMS speed of the oxygen molecule. The RMS speed of the molecule is 483.2 meters per second. From the above numerical example, we can say that the RMS speed of the gas molecules is of the order of the speed of sound at that temperature. This speed depends on the mass of the molecule at a given temperature. Lighter molecules exhibit greater speed because the RMS speed is inversely proportional to the mass of the gas molecule. As the RMS speed increases, the diffusion of the molecules of the gas increases. The diffusion is also inversely proportional to the mass of the molecule at the given temperature, because at the given temperature, the average kinetic energy of the gas is fixed. To understand the law of equipartition of energy, first, we assume that the considered gas is in thermal equilibrium, and it consists of molecules of negligible size and are hard spheres. We will consider a monoatomic gas and that the molecules of the gas can move randomly in the space in all directions. Let Vx, Vy and Vz be the velocities of a gas molecule on the x-axis, y-axis and z-axis respectively. Then, the translational kinetic energy of a single molecule is Et is equal to half mvx square plus half mvy square plus half mvz square. The number of independent terms in the expression of energy of a molecule is called its degree of freedom. In the expression of translational kinetic energy, there are 3 terms that can be treated independently. So, the degree of freedom of a molecule in the case of a monoatomic gas is 3. Note that each of the translational degrees of freedom corresponds to the motion of the molecule in a particular direction. If the molecule is moving in space, then it can move in 3 directions. Hence, the molecule has 3 degrees of freedom. If the motion of the molecule is confined to a plane, then the molecule can move in 2 directions. Hence, the molecule has 2 degrees of freedom. If the motion of the molecule is confined to a line, then the molecule can move in 1 direction only. Hence, the molecule has 1 degree of freedom. The degrees of freedom discussed so far are associated only with the translational motion of a molecule. If a molecule has other modes of motion, it will have a greater number of degrees of freedom. Now, if we consider a diatomic gas, such as O2, N2, then the 2 atoms of the molecules of these gases are assumed to be in the shape of dumbbells. That is, the 2 atoms are connected with some separation. Now, apart from translational motion, the diatomic molecule can rotate about its center of mass. Consider that the line joining the 2 atoms is along the z-axis. Then, the axis of rotation will be perpendicular to the z-axis. That is, the axis of rotation will be along the x-axis and y-axis. Because the molecule has 2 different types of motions, it has rotational kinetic energy in addition to translational kinetic energy. Since the molecule can rotate about 2 different axes, the rotational kinetic energy, ER, is equal to half Ix omega x square plus half Iy omega y square. The total kinetic energy of a diatomic molecule is the sum of the translational kinetic energy and rotational kinetic energy. Or, the total kinetic energy is ET plus ER, which is equal to half mvx square plus half mvy square plus half mvz square plus half Ix omega x square plus half Iy omega y square. In this expression, the number of independent terms is 5. So, the degree of freedom of a molecule in a diatomic gas is 5 when it has both translational and rotational motion and the molecule does not vibrate. Thus, the equation is true only when we assume that the molecule does not vibrate. But there are some diatomic molecules, like carbon monoxide, that exhibit vibratory motion along with translational and rotational motion even at moderate temperatures. The 2 atoms of carbon monoxide molecule are separated by some distance and they vibrate along its length by a small distance of r. Then, the vibration energy of the molecule involves kinetic energy of vibration and potential energy due to the compression or elongation of the 2 molecules. The energy due to vibration, EV, is equal to half mu dr by dt square plus half kr square, where mu is the mass of the molecule, k is the force constant, and dr by dt is the velocity of the atoms along the length of the molecule. The total energy of the molecules is equal to the sum of translational kinetic energy, rotational kinetic energy, and energy due to the vibration. That is, E is equal to half mvx square plus half mvy square plus half mvz square plus half ix omega x square plus half iy omega y square plus half mu dr by dt square plus half kr square. In this expression, the number of independent terms is 7. So, the degree of freedom of a molecule of a diatomic gas when the molecule is vibrating is 7. The law of equipartition of energy states that, in thermal equilibrium, the average energy of a molecule in a gas associated with each degree of freedom is equal to half kBT. According to the law of equipartition of energy, the average energy of a molecule of a monoatomic gas is equal to 3 by 2 kBT because the degree of freedom of a molecule in a monoatomic gas is 3. In the case of a diatomic gas, if the molecule does not vibrate, then the average energy of a molecule in a diatomic gas is equal to 5 by 2 kBT because the degree of freedom is 5. In the case of a diatomic gas, if the molecule vibrates, then the average energy of a molecule in a diatomic gas is equal to 7 by 2 multiplied with kBT because the degree of freedom is 7. The total average energy of a gas is called the internal energy of the gas. Consider that the sample contains n moles of gas. We know that each mole of a gas has an Avogadro's number of molecules. Then, the internal energy of n moles of a monoatomic gas, U, is equal to n into Na into 3 by 2 kBT. Since Na into Kb is equal to R, we get the internal energy of a monoatomic gas, U, is equal to 3 by 2 nRT. The internal energy of n moles of a diatomic gas, if it is not vibrating, is U is equal to n into Na into 5 by 2 kBT. Since Na into Kb is equal to R, we get the internal energy of a diatomic gas, if it is not vibrating, U is equal to 5 by 2 nRT. The internal energy of n moles of a diatomic gas, if it is vibrating, is U is equal to n into Na into 7 by 2 kBT. Since Na into Kb is equal to R, we get the internal energy of a diatomic gas, if it is vibrating, as U is equal to 7 by 2 nRT. Finally, in the case of polyatomic gases, the number of independent terms in the energy equation, degree of freedom and internal energy of the gas depend on the arrangement of the molecules. The specific heat capacity of a substance is defined as the amount of heat energy required per unit mass to change its temperature by 1 unit. That is, S is equal to 1 by m multiplied by dq by dt. where m is the mass of the substance, and dq is the heat absorbed for a small change dt in the temperature. The amount of heat energy required per 1 mole of substance to change its temperature by 1 unit is called molar specific heat capacity. That is, C is equal to 1 by N multiplied by dQ by dt, where N is the number of moles of the substance. According to the first law of thermodynamics, delta Q is equal to delta U plus P dV, where delta Q is the heat energy exchanged. U is the change in internal energy. P is the pressure and dV is the change in volume. The molar specific heat capacity at a constant volume, CV, is equal to 1 divided by N multiplied by dQ by dt. The subscript V on the right side indicates that the heat is absorbed at a constant volume. When the volume is constant, the work done, PdV, is equal to 0. And the heat energy exchanged is equal to the change in the internal energy. Then the specific heat capacity at a constant volume is equal to 1 by N multiplied by du by dt. Let this be equation 1. Then the molar specific heat capacity at a constant pressure can be found by using the relationship between Cp and Cv. That is, Cp minus Cv is equal to R. Therefore, Cp is equal to Cv plus R. Let this be equation 2. By using the above relationship, we can find the specific heat capacities of a monoatomic gas. In the case of a monoatomic gas, a molecule has 3 degrees of freedom. The average energy of the molecule according to the law of equipartition of energy is 3 by 2 multiplied by kBt. 1 mole of gas contains Avogadro's number of molecules. Then, the average energy of n moles of monoatomic gas is equal to N into Na into 3 by 2 kBt. This energy is equal to the internal energy of the gas. Since the product of the Avogadro's number, Na, and Boltzmann's constant, Kb, is equal to the universal gas constant R, we get U is equal to 3 by 2 nRT. According to equation 1, the molar specific heat capacity of a monoatomic gas at a constant volume, Cv, is equal to 1 by N multiplied by du by dt of V. By substituting the internal energy of a monoatomic gas in the above equation, we get the specific heat capacity at a constant volume. Cv is equal to 3 by 2R. As per equation 2, we get Cp is equal to Cv plus R. Hence, we get Cp is equal to 3 by 2R plus R, which is equal to 5 by 2R. Gamma is equal to the ratio of the specific heat capacity at a constant pressure Cp to the specific heat capacity at a constant volume Cv. On further substituting, we get gamma is equal to 5 by 2R by 3 by 2R, which is equal to 5 by 3 or 1.67. Thus, for monoatomic gases, the ratio of specific heat capacities is equal to 1.67. Now, let's look at the specific heat capacities of a diatomic gas. In the first case, we will consider that the molecule is not vibrating and that it has only translational and rotational degrees of freedom. Then, the number of degrees of freedom is 5. Then, according to the law of equipartition of energy, the average energy of a molecule is 5 by 2 kBT. Since 1 mole of gas contains Avogadro's number of molecules, the average energy of n moles of a diatomic gas is equal to n into Na into 5 by 2 kBT. This energy is equal to the internal energy of the gas. Since the product of the Avogadro's number Na and Boltzmann's constant Kb is equal to the universal gas constant R, we get U is equal to 5 by 2 nRT. The molar specific heat capacity of a diatomic gas at a constant volume Cv is equal to 1 by N multiplied by du by dt. By substituting the internal energy of a diatomic gas in the above equation, we get the specific heat capacity at a constant volume Cv is equal to 5 by 2R. From equation 2, we get Cp is equal to Cv plus R. Thus, Cp is equal to 5 by 2R plus R, which is equal to 7 by 2R. Gamma is equal to Cp by Cv. On further substituting, we get gamma is equal to 7 by 2R by 5 by 2R, which is equal to 7 by 5 or 1.4. Hence, the ratio of specific heat capacities for a diatomic gas when the molecule is not vibrating is 1.4. Now, in the second case, we will consider a diatomic molecule that has vibrational motion as well. The number of degrees of freedom in such a case is 7. Then, according to the law of equipartition of energy, the average energy of a molecule is 7 by 2 kBT. 1 mole of gas contains Avogadro's number of molecules. Then, the average energy of n moles of a diatomic gas is equal to n into Na into 7 by 2 kBT. This energy is equal to the internal energy of the gas. Since the product of the Avogadro's number Na and Boltzmann's constant Kb is equal to the universal gas constant R, we get U is equal to 7 by 2 nRT. The molar specific heat capacity of a diatomic gas at a constant volume Cv is equal to 1 by N multiplied by du by dt. By substituting the internal energy of a diatomic gas in the above equation, we get the specific heat capacity at a constant volume Cv is equal to 7 by 2R. From the relationship between Cp, Cv and R, Cp is equal to Cv plus R. We get Cp is equal to 7 by 2R plus R, which is equal to 9 by 2R. Gamma is equal to Cp by Cv. Substituting the values, we get gamma is equal to 9 by 2R by 7 by 2R, which is equal to 9 by 7 or 1.29. Hence, the ratio of specific heat capacities of a diatomic gas when the molecule is vibrating is 1.29. In the case of polyatomic gases, the molecule has 3 translational degrees of freedom and 3 rotational degrees of freedom, since the molecule can move in the space in 3 dimensions and can rotate about the 3 axes of rotation. And the molecule has certain number 2f of vibration degrees of freedom for f modes of vibrational motion. We have f degrees of freedom associated with elastic potential energy and f degrees of freedom due to the kinetic energy of vibration, which totals 2f degrees of freedom. 1 mole of gas contains Avogadro's number of molecules. According to the law of equipartition of energy, the average energy of a molecule of a polyatomic gas is equal to 6 plus 2f by 2 into kBt, which is equal to 3 plus f whole into kBt. If we have n moles of gas, the average energy of all the molecules of the gas is equal to the internal energy of the gas. Since the product of the Avogadro's number, Na, and Boltzmann's constant, Kb, is equal to the universal gas constant R, we get U is equal to 3 plus F whole multiplied by nRT. The molar specific heat capacity of a polyatomic gas at a constant volume Cv is equal to 1 by N multiplied by du by dt. By substituting the internal energy of a polyatomic gas in the above equation, we get the specific heat capacity at a constant volume Cv is equal to 3 plus F whole multiplied by R. From the relationship between Cp, Cv and R, Cp is equal to Cv plus R. We get Cp is equal to 3 plus F whole into R plus R, which is equal to 4 plus F whole multiplied by R. Thus, gamma is equal to Cp by Cv, or 4 plus F whole into R by 3 plus F whole into R. Hence, the ratio of specific heat capacities of a polyatomic gas is 4 plus F by 3 plus F. At ordinary temperatures, the predicted values of Cp and Cv are in good agreement with the actual values, according to the law of equipartition of energy. But at higher temperatures, there are some polyatomic gases such as ethane and methane, for which the predicted values are not the same as the actual values. In such cases, we should include the degrees of freedom in the vibration mode. Now, let's learn about the specific heat capacity of solids. In the case of solids, the molecules don't have translational motion and rotational motion. The molecules simply vibrate in the 3 dimensions. When a molecule is vibrating, it has 2 degrees of freedom for each mode. One associated with potential energy and the other associated with kinetic energy. Then, according to the law of equipartition of energy, the average energy of each molecule from each mode is equal to 2 times half kBT. Then, in 3 dimensions, the total average energy of the vibrating molecule of a solid is equal to 3 kBT. For 1 mole of a solid, the number of molecules is equal to the Avogadro's number, and the average energy is equal to Na into 3 kBT. Since the product of the Avogadro's number Na and Boltzmann's constant Kb is equal to the universal gas constant R, we get the total average energy of the molecules as 3RT. This average energy of the molecules is equal to the internal energy of the molecules. The change in the volume of solids is negligible, and hence the heat energy exchanged is equal to the change in the internal energy. Then the specific heat capacity of the solid can be found by substituting the internal energy in the specific heat capacity formula. C is equal to U by T equal to 3RT by T. Thus, we get the specific heat capacity of the solid as 3R. In the case of solids, the predicted values are in agreement with the actual values of the solids. Now, we will discuss the specific heat capacity of water. To calculate the specific heat capacity of water, we will treat water as a solid. A water molecule has 3 atoms, and every atom has an average energy of 3 kBT. The total energy of the water molecule is equal to 9 kBT. The internal energy of 1 mole of water is equal to Na into 9 kBT, which is equal to 9 RT. By substituting the value of internal energy in the specific heat capacity formula, it is equal to 9R. This value is in agreement with the observed value. That is, 1 mole of water contains 18 grams, and the observed value of the specific heat capacity of water is 4.2 joules per gram per Kelvin. So, the molar specific heat capacity of water is approximately equal to 75 joules per mole per Kelvin. That is, the predicted value and the observed value are the same. All these predictions of specific heat capacities are based on the classical law of equipartition of energy, where the specific heat capacities are independent of temperature. But, practically, this is not true. As the absolute temperature tends towards 0, the specific heat capacity of all substances approaches 0. This is because, at low temperatures, the degrees of freedom get frozen. This was explained by quantum mechanics because it requires a minimum non-zero energy before the degrees of freedom comes into play. The molecules of a gas move with an average velocity of the order of the velocity of sound. But when a perfume bottle is opened, it takes longer for the diffusion of molecules to faraway places. This is because the molecules undergo frequent collisions with other molecules of the gas, and as a result, continuously change their paths. The average distance travelled by a molecule between collisions is called the mean free path. Let us find an expression for the mean free path of a gas molecule. According to kinetic theory, it is assumed that the molecules of a gas are spherical in shape. Let d be the diameter of a molecule and let it move with an average velocity of v bar. When the molecules are in motion, they undergo collision with other molecules which come within a distance d between their centers. Then, the effective region of the collisions is circular in shape. The effective collision area is equal to pi d square. In t seconds, a molecule can travel a distance of v bar t, and the effective collision area forms a cylinder. The molecule undergoes collision with all the other molecules whose centers lie within the volume covered by the effective collision area. The volume of the cylinder covered by the effective collision area in t seconds is equal to pi d square v bar t. Let the number of molecules per unit volume be NV. Then, the number of collisions in time t seconds is NV pi d square v bar t. Hence, number of collisions in 1 second is equal to the total number of collisions divided by time, which is equal to NV pi d square v bar. This is called collision frequency. The time interval between successive collisions is equal to 1 by the number of collisions in 1 second, which is equal to 1 by NV pi d square v bar. The average distance travelled by the molecule between two successive collisions is called mean free path. That is, mean free path is equal to the average velocity of the molecule multiplied by the time interval between successive collisions. Thus, mean free path is equal to v bar into 1 by NV pi d square v bar, which is equal to 1 by NV pi d square. While deriving this expression, we have not considered the motion of the other molecules. If the motion of the other molecules is considered, then, while calculating the collision rate, the average relative velocity of the molecules need to be taken into account. Now, we will calculate the average relative velocity of molecules. Let us consider two molecules moving with velocities v1 and v2 in different directions. Then, the relative velocity of the two molecules is v relative is equal to v1 minus v2. The magnitude of the average relative velocity, v relative bar, is equal to the square root of v relative bar dot v relative bar. Thus, v relative bar is equal to the square root of v1 minus v2 dot v1 minus v2. Simplifying, we get v relative bar is equal to the square root of v1 dot v1 minus 2 into v1 dot v2 plus v2 dot v2. Since the motion of the molecules is random, the angle between V1 and V2 can vary between 0 degrees and 180 degrees. As such, the average of V1 dot V2 must be equal to 0. If we assume that the average velocities of all the molecules are the same, then V1 is equal to V2 is equal to V bar. By substituting the average velocity as V bar and neglecting the uncorrelated terms with respect to angle, we get the average relative velocity as square root 2 multiplied by average velocity, or square root 2 V bar. As a result, the number of collisions has increased by root 2 times the number of collisions when compared with molecules that are stationary. The effective volume swept by the molecules has also increased by root 2 times. The resultant mean free path is L is equal to 1 by square root 2n V pi d square. So, the mean free path depends on the number of molecules per unit volume and the size of the molecules. That is, mean free path is inversely proportional to the number of molecules per unit volume, or L is inversely proportional to NV. And it is also inversely proportional to the square of the diameter of the molecule, or L is inversely proportional to d square. The number of molecules per unit volume can be calculated using Avogadro's number and the ideal gas equation. The number of molecules per unit volume, NV, is equal to N times the Avogadro's number, Na, divided by V, where N is the number of moles of the gas. Na is Avogadro's number, and V is the volume of the gas. From the ideal gas equation, the volume of the gas, V, is equal to nRT by P. Then, the number of molecules per unit volume can be written as NV is equal to N into Na by nRT by P, which is equal to Pna by RT. Then the mean free path of the molecules can be written as L is equal to RT by square root 2 pi NAD square P. Hence, we see that the mean free path is directly proportional to the absolute temperature of the gas, and is also inversely proportional to the pressure of the gas.